Welcome to today's webinar, introducing Coreform IGA for Abaqus, which is still FEA with no meshing. My name is Matt Cederberg. I'm the CEO of Coreform, and I'll be presenting the webinar today along with Greg Vernon, the Chief Engineer at Coreform. But a bit about my background, I've been spending my entire about 2-decade career trying to help close the gap between CAD and simulation. My first company, T-Splines, was focused on introducing a new CAD technology that introduced ways to make more efficient and watertight CAD models that's now used in Autodesk's Fusion 360 and other product lines. And Greg Vernon is a FEA engineer that has over a decade of experience and is now leading the effort at Coreform to help introduce isogeometric analysis. So the agenda today, we will give a little bit of historical context to introduce what finite element analysis is and its one flaw. Then we will introduce Coreform IGA for Abaqus, talk about the question we get more often than any others, which is where did my mesh go when using this approach? Introduce the current capabilities, give a live demo, and then have some time for Q&A. And feel free to ask questions throughout the webinar. We'll either type them back or answer them at the end. So finite element analysis is the trusted method that's been used for decades now to predict how products will perform before they are built. So you see this example of the Hubble Space Telescope. Of course, FEA is used across industries, including automotive, defense, aerospace, consumer products. And it's proven and useful because it's simple, it's well understood, it's robust. There's a lot of good qualities of the finite element method. The one flaw is that it does not use the same mathematical basis that CAD does. And so as you're familiar with, if you're an engineer, then when you design models, you're using CAD software, and these are designed using smooth splines and analytic surfaces. And ironically, the very first thing that you do when you want to run a simulation to predict how that CAD design will behave after it's manufactured is you change the design. You remove potentially critical features that may significantly impact the performance of the part just because you need to have a geometry that you can get a suitable mesh on. And that process of creating that mesh not only gives you a less precise design, but it can also be very time intensive. In fact, that whole process of meshing and model preparation consumes most of simulation time. So various studies have come out that for high quality simulation, up to 80% of the total time to solution is spent preparing the model, not solving that. This number was based on a survey done a couple of decades ago by Sandia National Laboratory. And in the hundreds of interviews that Coreform has done with engineers, this number, if anything, has gone up as designs have become more complex. And that chasm has limited access to simulation. And in the past, that's been significant because it's limited the broadest use of this high fidelity simulation to analysts and prevented CAD engineers from accessing it. And this problem is becoming even more acute as we enter the era of artificial intelligence. As agents and multi-agent workflows are being introduced, this requirement to insert the need to create an approximate mesh of your CAD model, which requires human discernment and human interaction, really does severely limit the ability of CAD agents or AI agents to integrate and fully leverage simulation. Another consideration with meshing is it does force a choice between labor and efficiency. So the two ways to mesh solid models are by using hex elements or TED elements. Hex elements are preferred because they're more accurate, robust, and performant, but they can be very time-consuming to create. So many analysts just use TED elements, which can be automatically generated, but they're very expensive to commute and can be less robust. We'll show an example later in the presentation about the trade-off between these two approaches. So given that was the state of things, about 20 years ago now, Thomas Hughes from the UT Austin introduced a new approach called isogeometric analysis, which reconsidered the idea of finite element analysis and wondered, well, what if rather than having a completely different math basis for CAD simulation, what if we did simulation directly on the CAD geometry using the smooth higher order basis of splines that's used in CAD? And so for the last 2 decades, there's been thousands of research papers published investigating this new method. And it's been somewhat surprising that not only does that give you the chance to operate directly on the CAD, but there are some superior properties of using that new spline basis that it actually is more accurate per degree of freedom than traditional FEA. And so that's what we're introducing today is an integration of this new ability to run a simulation directly on CAD, escaping this loop that you're forever caught in running FEA, where you need to defeature, mesh, and repeat, and escaping that so you can just run simulation directly on the CAD data, which leads to the ability to have tighter design iterations and more accurate simulations. And as we noted, as of this week, we now have this approach integrated with Abaqus. And now I'll turn the time over to Greg to explain the details of what's available today with this integration and give a live demo.
Yeah. Thanks, Matt. Yeah, I'm glad to be here and I'm excited to present to you guys today. Yeah, so as Matt said, Coreform IGA for Abaqus is a product we just released this week, and that's why you're all here. But it integrates our Coreform IGA technology into both the Abaqus CAE and the Abaqus standard solver that you're familiar with. And that allows us to then perform this analysis directly on CAD. And really, the method behind or the novel technology behind it is what we call volumetric trimming. And it's based on that modern BREP CAD is based on what's called surface trimming, where we take these patches of spline surfaces and then we define trimming curves inside of them that define how a specific surface is extracted from that background spline. And then the combination of those trimmed surfaces produces this boundary representation. Of course, for solid finite elements, we need a volumetric representation. So what we've done at Coreform is we've extended that surface trimming idea into the volumetric trimming idea, where we now trim on the volume. And then that gives us a parameterization that we can perform simulation analysis on. And so where'd the mesh go? Again, that's one of the questions that we get asked most often at Coreform. And the mesh is still there. It's just kind of hidden from like the workflow perspective of a user. We start with the CAD model. We drop this CAD model again in this background bounding spline volume grid. So similar to the background spline surface in CAD trimming. We then trim that smooth spline grid to the CAD volume, like a Boolean operation to produce that interior trimmed volume. And then that's what we perform that simulation on. So the mesh is always still there in the background for the computational analysis, but just that process of dropping it in that smooth spline grid removes a lot of the manual effort in producing these meshes. And then we integrate this mesh into Abaqus via a user element. So from a user perspective, if you're in Abaqus CAE and you submit your job, there are two things that go off. One, we go off and we run Coreform IGA mesh, which is our proprietary technology that builds that trimmed spline mesh. And that produces databases that supply a user element library that we ship with our product. We also write out a standard Abaqus input deck that then includes this Coreform IGA mesh via an include keyword. And then during the solve, Abaqus standard provides material data to our user elements, and then we provide back element stiffness matrices or anything else that Abaqus standard needs for its current operation. And so that specifically uses the UEL mat functionality of Abaqus, where the mat aspect of their user elements is what provides the material data to Coreform. We also get asked a lot, like, when should I use Coreform IGA for Abaqus? What's the target? And we kind of say that there's kind of three areas where Coreform IGA for Abaqus really shines. It's when you have complex geometry that's challenging to build meshes on. So like this vehicle suspension with a caliper subassembly model on the left. If you have complex physics, such as large deformation, nearly compressible, nonlinear elasticity, contact, self-contact, metal plasticity, Or if you have engineers who aren't meshing experts and need solutions that are robust and converge well for nonlinear analyses, which we'll talk about in a little bit on the right. Yeah, so as I mentioned, in this case, we have like this caliper subassembly where that's the geometry that we cared about to understand in this kind of break analysis. And rather than spending a lot of time to defeature that model, it took me 20 hours to do a defeaturing because I only had the step file. Because I didn't have the native CAD, I couldn't just turn off the fillets. So it took me 20 hours to feature that model so I could build a hex mesh on it. It ended up actually removing the locations where you can see on the right in the full IGA model, where I've got stress concentrations on some shoulder fillets. Those fillets are gone from my FEA model and would require some post-processing analysis on my end to recover those predictions. Instead, I can just, in less than a minute, have a mesh, run my simulation, and get the results directly on that CAD geometry. Um, and then as far as supporting complex physics, again, as I mentioned, this is a large deformation, nonlinear compressibility. It's a rubber gasket type of component, frictional self-contact. You can see also as I import this geometry into Abaqus CAE, it warns me about the geometry being imprecise. That can cause a lot of issues if you're trying to build a hex mesh as you're doing partitioning. If your partitions start to interfere with some of those imprecise entities, it can cause issues that make it unable to proceed forward without healing or additional cleanup. And this model, as you can see in the middle example here, is able to trim mesh just fine with no issues. Um, and then additionally, I mentioned for non-experts, we had a summer intern this year who had just finished off her freshman year at the School of Mines and the engineering program there. And she looked at an interior cervical plate analysis following an ASTM standard. And she tried three different approaches. She tried tap meshing the model first. The meshing was automatic and simple, but when she then ran the simulation, she had challenges with some spurious contact stresses. And we were able, with my assistance, to be able to get this simulation to end up running. But again, that took someone who has experience running FEA and especially nonlinear to be able to recover those solutions. She also spent some time trying to build a hex mesh, and she used our other product, Coreform Qubit, to build a body fit hex mesh there. Took her about 40 hours to build that hex mesh by hand. Again, I was able to come back in afterwards and spend about 3 hours to build the mesh. But again, I've got a lot of experience building hex meshes that that is what allowed me to run that faster. And then lastly, she took the exact same setup she had been doing, and instead of tep meshing or hex meshing, she just ran Coreform IGA mesh on it, and it automatically meshed. And she ran the simulation, and without any kind of tweaking of solver parameters or contact settings, the nonlinear analysis just solved for her, and she was able to extract out the stresses in those fillets, and she was able to make a prediction on the fatigue life of this plate. As far as the capabilities go, we have some production capabilities today, but the way that we built this out, because we're using UEL mat, as we add functionality to um, Coreform IGA for Abaqus, it's immediately becoming available, or different features are becoming available immediately for you to test out and try. So while we today support linear static stress, some relatively small assemblies, we do have compatibility with having FEA meshes and stuff like connectors, fasteners, couplings, thermal expansion, and thin wall parts. We also then have beta functionality for these more general nonlinear problems like large deformation, mechanical contact, plasticity, nearly compressible elasticity, and also some linear perturbation studies like frequency extraction, random vibration, response spectrum, and more. So those are just available to users who want to explore some of the more beta functionalities. We're going to go into a live demo here shortly on this glass to metal seal example here. But what I want to point out with this as I walk through is that I already have the simulation run and I've already got the problem set up. So we'll miss the step where I've imported the CAD geometry from a step file. And again, as I import it, it comes in with a lot of imprecise geometry, which again, traditionally I might consider trying to defeature or heal. But we're also able to use all of the, or several complex material models or material behaviors. We're able to assign our load and boundary conditions directly on the CAD geometry. And then IGA meshing is just a seamless process within the workflow. And then we'll show some quick results. So let's maybe shift over then to the live demo here. I'm going to share my screen. Um, I'll start off with just walking through or showing the documentation I'm currently building. So this example is, or this demo, I'm building an example in our documentation, but it does exercise some advanced beta capabilities that aren't yet officially released, but demonstrate um, the the workflow. This is a glass to metal seal that's derived from some public papers that actually my mentor, when I was early in my career, had written. But what I want to point out is that there are complex material models. There's thermal expansion, that's temperature dependent thermal expansion, temperature dependent Young's moduli, temperature dependent plasticity models, that because we use UEL mat, those are all available to users to test out. So to clarify, then I just want to reinforce that this demo is going to demonstrate beta functionality that's beyond the release functionality of linear static stress. So this is our assembly geometry. One of the things I've done already is that I want to have a contiguous mesh traditionally between the seal and like the pins as well as the header. There's different ways you could do this modeling. You could also model its interfaces with frictional contact, but for this first setup, I wanted to model it as if it was contiguous. So I did the workflow where I imported my CAD geometry. I had a whole bunch of different parts. I went to my assembly mode, and then I used the Boolean merge operation to merge all those parts into a single part with multiple cells. So if I color this by cells, you'll see that there's, I think, 14 different cells, but they're all part of a single part. And so we utilize that information to then build essentially a weakly enforced contiguous solution. If I go to the property module, you can see I've already assigned some materials here. But if we look at, say, like the alloy 52 material, which is used for the pins, I've got mass density. If I wanted to do a true thermal analysis, or if I wanted to do like a implicit dynamic analysis, I could use the mass density for that. Here I just got a temperature independent elasticity, but I've got an expansion coefficient, which is constant, and then I've got my metal plasticity for my 304 L bar. I've got my temperature dependent plasticity data, as well as temperature dependent thermal expansion. And then similarly for the glass, I've got temperature dependent expansion coefficient. So again, UEL mat allows us, the UEL mat connection between Coreform IGA and Abaqus is what allows us to then utilize these material models directly from Abaqus. So if you already have material models, you don't have to worry about changing them or converting them to a different solver. And then I ran 3 different steps here, essentially to cool this from where the seal is being set in down to room temperature, and then cooling it and heating it through like a thermal cycle. And these are static general, but these have nonlinear geometry. And then I'm using the unsymmetric solver for these due to the nonlinearities of this problem. To then enforce or remove the rigid body modes, I have a distributed coupling between a reference point and then this outer annulus surface here. So again, this demonstrates the ability of Coreform IGA for Abaqus to utilize traditional reduced order model approaches such as couplings. And then I've applied my boundary conditions, again, just applying a boundary condition to that reference point of my couple, and then applying a predefined field that then changes over time for that global temperature. So it's essentially assuming kind of a thermal soak for that load condition and a uniform distribution of temperature. And then the last step here is going to be defining the mesh. And what I want to point out is, so here I've set my model up that I could now automatically build just a mesh on this. And so the pink regions will automatically tech mesh and the yellow region will hex mesh. And some of the challenges you'll see is that just because those elements are incompatible, normally you'd throw in tie constraints between those interfaces. And one of the challenges with the intent meshing is if I don't do any defeaturing, what we'll end up seeing is that I really care about trying to predict whether or not my seal is going to crack. And I care about the interfaces between the pins and the header and the seal to see how those interfaces affect whether cracking is going to occur. But with body fit meshing, majority of my elements are actually not going where I actually care about them. I'm spending a lot of element budget on a thin region of my geometry that really doesn't matter. So this is where even with traditional tap meshing, you'd likely still want to spend time cleaning up this model just so that you have a more efficient solve. That I want to put more elements in this region. And of course, I might decide that I want to build a hex mesh on these pins. And so then that takes more manual time for me to then define that hex mesh on those pins to get that right. If I want a more structured mesh to have a more uniform result on my seal, I'm going to have to spend time partitioning my seal for that. So those are just some of the engineering considerations that occur with traditional finite element methods. But here I'll go ahead and delete my mesh and I'll show you what Coreform IGA for Abaqus allows us to do. You can see here, this is the Coreform IGA for Abaqus custom application that we ship. And there's a button here to create Coreform IGA meshes. I can just click that button. And then inside of the GUI dialog here, I can just insert a target mesh size. I can preview that mesh size. If I want a finer mesh, I can define a finer mesh. Right now, we do only support global mesh sizes. We currently are working on adding local adaptivity. And in fact, since the release of this of Coreform IGA for Abaqus on our internal development branch, we have merged our local adaptivity capabilities. So that'll be something to keep an eye out for in the future. But this mesh looks good to me. I'll just go ahead and say, okay, you build that mesh. And that's it. From a user perspective, I'm done building my mesh. I'm done meshing. The next or last step for me to do is just to create and submit my job. Here I've already created a job. So I'll just edit this. And I can essentially just choose to run, say, parallel for Abaqus and parallel for the volumetric trimming operation. I don't have time to run this analysis during this call, so I've pre-computed the results, which we can look at in the visualization module. Let me turn off my mesh real quick. No. Switch. So this is an initial release. So we are trying to kink out or work out some kinks in some of the user displays. But if we look here, you can see my background grid on top of my simulation result. I've created a cylindrical coordinate system. So here, looking at the radial displacement of my header geometry at the final time step, and also look at then, say, my stress. Maybe I want to look at the max principal stress. And maybe specifically, I want to look at it in the glass seal. And then given the millimeter ton second unit system, I want to set my bounds here to 35 megapascals, the maximum value. And so based on a kind of a simple 35 megapascal tensile stress failure criteria, I can start to see that I've got some regions that are essentially saturating at that tensile stress. So I might expect to see cracks occurring at some of these gray regions. You can see those are still really tightly bounded to the circle or to those holes. So something to definitely watch out for, but I can start to see an entire region connecting two of those holes. Um, So that's just the ability to use Coreform IGA for Abaqus to set up a model, analyze it, and look at results. So how can you use Coreform IGA for Abaqus? As I mentioned, this just came out just this week. It does rely on the latest hotfix from Abaqus. So your Abaqus environment needs to have Abaqus 2026 hotfix 5. Also, currently only supports Abaqus Standard. We don't yet support Abaqus Explicit. If you're interested in Abaqus Explicit, we'd love to hear from you and talk more about your needs. Um, we also provide a license for this plugin. So in addition to your Abaqus, you need a license for Coreform IGA for Abaqus. You can either license that through us or through a growing list of our reseller or Abaqus resellers. There is early adopter pricing available now if you're interested to try out these initial few releases. Also mention that the from compatibility, if you have importers for Abaqus CAE for different CAD files or CAD connectors, you can still use those. Otherwise, any other CAD that will import into Abaqus CAE, specifically BREP CAD, so STEP, ASIS, not fastened geometries like STL, those will work. And it's also supported on both Windows and Linux for Solve and the GUI.
Okay. Thank you very much, Greg. All right, now we have time for some questions. We've got a few that have come in already. If you have others, feel free to type them in. Question about the analysis you ran, Greg. How long did that take? So you might be muted, Greg.
Yep, sorry, I was muted. Yep, that analysis took 45 minutes to run. I set a maximum time step increment of zero point 0.1, and I started at 0.01 with automatic stepping. So without any cutbacks, it stepped up to my maximum time increment and then stepped at that zero point 0.1 time increment for each of the steps. So if I didn't want as much time resolution, it would have solved faster.
Okay. Is Coreform IGA compatible with all material models available in Abaqus Standard?
No, there are a few material models. I don't know them off the top of my head, but there are a few material models that are not supported by UEL MAT. My recommendation is that if you go to the Abacus documentation and look for UEL MAT, it'll provide lists of things that are and are not supported. I do believe that it's fairly limited on the things that are not supported. I think there's like a concrete crush model that maybe is not supported. But otherwise, if it's supported by UEL MAT, there's at least beta functionality in Coreform IGA for Abaqus. We're also limiting ourselves to saying what's officially supported, but based on our published documentation for our verification manual. So all material models I showed today, like the everything from density to expansion, the plasticity is considered beta for us just because we don't feel that we yet have sufficient verification documentation available publicly. But yeah, that's the kind of the limiting factor is what's supported by UEL MAT.
Okay. In Abacus, I validate my model with a mesh convergence study. What's the equivalent verification procedure in Coreform IGA for Abacus?
Yeah. You can still do a mesh convergence study in Coreform IGA for Abaqus. Coreform IGA is still a Galerkin method, so it inherits all of the rich mathematical theory and background of finite elements. And so things like convergence to respective norms work for mesh refinement as well as for degree refinement. As I said, we are working on providing local adaptivity, which will provide more knobs for you to do conversions on localized regions without the enormous compute expense of doing global refinement. But yeah, that same concept exists in Coreform IGA for Abaqus.
Okay. Okay, if I have a multi-part assembly, do I have to use the same global mesh and mesh size for the entire assembly?
No, each instance can have its own mesh. So you can, if you use instance-based modeling, you could provide a different mesh per instance. Here I did a single part, multiple cell approach as a way to have an efficient modeling of the interfaces between the pin, seal, and headers. And with our local refinement, that's coming out will be able to then define like a local mesh on, say, like the pins. But today, per part or per instance, you have a single mesh. So an assembly can have multiple mesh sizes.
Okay, question from Igor. You missed the first part of the presentation. Can we get access to a recorded session and detailed documentation about the technology? Yes, we will send a recording out. And yes, we do have detailed documentation. And as we send out the recording, we'll also send a link for you to talk with us. And we'd love to have conversations with you to understand if the technology is at a spot where it would provide benefit for you today. And we'd love to follow up with documentation as you investigate this further. Um, okay, question from Aaron. As we do updates for Coreform IGA, will that be tied to Abaqus's release schedule, or will we be updating this plugin independently and potentially on a faster schedule?
Yeah, there will be some dependency on Abacus as far as some of like the very latest functionalities. So as they expand capabilities for UEL Mat, there'll be some links to those. But our plan is that there's a lot of space even today with the current UEL Mat functionality for us to grow and develop features for. So we intend to have a very quick development cycle as we add these new features. If anyone's familiar with us as well, our downloads page, we have multiple development releases per day with our latest functionality that users on the cutting edge can work with us to test out new capabilities. And we're expecting to have official releases approximately every month. Um, we'll see if we're able to maintain that pace, but that's kind of from the features that we have coming down the pipeline, we're expecting that for the foreseeable future to release every month and then maybe have some aligned releases with Abacus releases.
Okay. Question for someone who says, I'm a big fan of Abaqus, but out of curiosity, will you release Core from IGA for other CAE software? So we already have been integrating Core from IGA with other government codes. And our vision, as you can imagine, after seeing the potential of IGA, we really believe that this is the next generation of finite element analysis. And so we are very interested in integrating this with as many CE softwares as possible. And so if you use other software or if you are writing other software, we'd love to talk with you and discuss how we can support an IG workflow with your software as well. Okay, what's the level of accuracy of the result when compared to a conventional FEA model, Greg?
Yeah, so that's a hard one to answer in that being Galerkin methods will typically converge to effectively the same answer for every problem. Kind of the question comes down to then accuracy per degree of freedom. And what I'll say is that we do have in our documentation, we have our verification manual where we show convergence to several problems. And so I think what's probably best is just to say that we can be as accurate as traditional FEA, and if you consider not defeaturing, you could argue more accurate to traditional hex meshing approaches. But we encourage you to look at our verification manual and review the results for yourself.
Okay. Does this method come with element deletion method today?
Yeah, today it does not. But I will say that again, because Coreform IGA is a Galerkin method, it is a finite element method. Anything that you can do in finite elements, you can do in Coreform IGA from a theory perspective. In our own internal research codes, we've demonstrated element deletion before for like a projectile impact application and conversion to particles on failure. So we've definitely demonstrated we can do this with this method. It's just not implemented today in Abaqus. If you are interested in that, we encourage you to reach out to us and explain to us your needs.
Does this technology work with connectors like spot welds? How sensitive is it to element size?
Yeah, to our knowledge, it does work with spot welds. We've got internal tests that test various different connectors all of the main connector like workflow functionality we test, including spot welds and point fasteners, and they appear to work pretty well. There likely is at least some um, requirement on mesh size that you can't have a mesh size that's grotesquely coarse, especially though as we add our local refinement. We expect that from a user perspective, you won't even need to worry about setting a mesh size. So I'd say in practice, I've not in practice found a requirement on mesh size.
Okay, and then another really interesting question, somewhat related. Does Coreform IGA work with sheet metal parts or only with solid components?
Yeah, so it depends on how you define sheet metal part. If it's a solid model of a sheet metal part, Coreform IGA does support that. Currently, our approach right now is just an all solids approach. We do again have theory demonstrating this same approach on shells, but we don't have a shell implementation today. Um, so as long as your CAD model is a solid, it works well. And then we've also, our verification tests have shown this as well, that when you use these high order methods, because of their ability to efficiently capture things like transverse shear stresses, they do really well in bending applications, even with less than one element through the thickness. So yeah, we find that many of our customers, especially with gigacasting, where they have bulky components that rather than being bolted or welded to a sheet metal component, it's integrated into a single cast part. We find that for those, the thin regions do really well with this approach.
Okay, an integration question. Since this is based on UEL mat, does that mean you're mapping the results to other simplified meshes for visualization?
Yes, it does mean that. If you aren't aware, user elements are not supported by Abaqus CAE for visualization. If you do write them, I think you get out a node element at the centroid of element, I think is how it's rendered. So the documentation points you to creating a kind of a tertiary mesh that you map your results onto. And we do the same thing today, where we create a hybrid linear hex and linear tet mesh, and we map our results onto that mesh to visualize in Abaqus CAE. We are working on some advanced visualization and output capabilities for peer review that remove that limitation. But that's still a beta functionality. You can test that functionality today if you'd like, but that's not yet released.
Okay. Another question about refinement levels. Inside the same part, can we change the mesh density today?
Not today in the released functionality, but I did mention one of the very first things we did after release was on our internal development branches. We've gone ahead and merged in local refinement. And so if you're interested to try out local refinement, and if you're interested in being on the cutting edge, we can work with you and there you can specify local regions to refine.
Okay. Okay, here's a great question. In a model that includes both IGA parts and conventional FEA parts, what sort of interactions can one simulate between those parts? Like connectors, couplings were mentioned in the presentation, but are things like penetration contact also possible?
Yeah. So as far as interactions, yes, essentially anything from a workflow perspective, anything that you can assign to geometry. So if you're in Advocacy AE and if you have like a connector and it says, pick the surface type for, the primary region, as long as you can pick a CAD entity for that on your IGA region, then it'll work. And that's just because we don't generate the mesh until after you submit. So there's not a node for you to pick, but we inherit those sets and make sure that we can handle stuff like connectors as well as contact. And so even like the initial overclosure, that's again, contact in general is a beta capability, but there is support for that notion. So yeah, everything there should be supported.
And again, we would love to follow up on conversations like that as they apply to your own parts. So again, as we reach out after the webinar, please reach out and we'd love to dig in deeper for your specific use cases. Okay, a question from John. What are the basis functions that we're using, and how does the basis change as the mesh is refined?
Yeah, so the basis we use, you may be familiar that Coreform's developed a technology called U-splines, which allow us to build meshes or smooth splines on unstructured meshes. Given that right now the meshes that we're showing today are all structured, we just use B-splines, and specifically tensor product B-splines. And you can choose the level of continuity that you want today. So you can choose have a maximally smooth cubic basis. We really only have done efficiency implementations up through cubics. So that's kind of where we recommend, but you can go to higher orders if you want. And then as you refine, if it's global refinement, it's just a globally refined B-spline. And then our adaptivity is based on truncated hierarchical B-splines.
A question from Simon. Do you have plans to extend this capability to the explicit solver? Maybe I'll just make a note there. So the Abaqus team has been extremely helpful in helping us do this integration. The the reason we are not integrated with explicit yet is that there is no corresponding VUAL mat functionality. And so that would require additional enhancements to what a third party can access through Abaqus. We're definitely getting a lot of interest in that. And if that is of interest to you, we'd love to hear it for you, and we can see how we can prioritize that in the future. Um, okay, let's see. Does the high
Yeah.
con Go ahead, Greg?
And I will say too that we're actually really excited about these methods in explicit because things like as you increase degree, your stable time step actually goes up rather than goes down. And so um, a lot of the issues that have maybe plagued higher order elements for explicit dynamics are resolved by these IGA methods. So we're actually very excited about the prospects of IGA for explicit analyses.
Okay, does the higher continuity of the spline basis function ever become a disadvantage? For example, in problems with sharp stress gradients, cracks, or material discontinuities?
Yeah, so I'd say that even in traditional FEA, right, so if you talk about continuity, unless your sharp kind of call it kink in your solution field, unless that's occurring at an element boundary anyways, then it's going to be occurring within a C infinite basis, like if it's inside of an element. And if, from a theory perspective, if you go back to like Stone-Weierstrass, as long as the function you're trying to approximate is continuous, you can use these smooth methods through refinement to still capture them to arbitrary accuracy. So what I'll say is that probably the biggest limitation today for those kind of problems is just in this current release, the global refinement approach, that if you want to then refine to try to get accuracy out of something like that, that you have to globally refine your solution, which means you're refining it in regions that you don't really care about. So I'd say that the solution to this is local additivity. And really continuity, in my experience, continuity has really no ill effect on your ability to approximate the solution when you consider solution accuracy per degree of freedom. And again, degrees of freedom are what show up in your linear systems. These degrees of freedom, um, or these linear systems, right? They have conditioning, which impacts your ability to solve both from a linear perspective and from a nonlinear perspective. Higher smoothness bases tend to result in higher or lower condition numbers, which are better. So better conditioning tends to mean that we converge really well. The example I showed today, most of the steps converge in a single Newton iteration. So they converged very efficiently, even as plasticity was starting to develop in the solution. So yeah, I don't personally see any challenges with continuity.
If I model the same nonlinear problem in Abaqus with a well-converged high-order mesh and in Coreform IGA, and the results disagree, what methodology do you recommend to determine which solution is physically correct?
Yeah, well, the to weasel out of the question, the answer is to run a physical test and and then use the physical test to provide insight to which one's more physically accurate. But I'll also say is that Abacus is a great tool, and Abacus has a lot of great functionalities for like computing error within elements, like the energy error or error norm and the error in the energy norms, stuff like that. There's a lot more maturity there than we have today in Coreform IGA for Abaqus for stuff like that. Um, we will get there, but that's one of the things you could look at is how accurate or what's the error that Abaqus can compute in its own solution, to get you a feel for how close to being converged your Abaqus solution is. But I will say, I mean, there are going to be some differences between your Abaqus results and the Coreform IGA results. We have different quadrature schemes. We do have different bases. So kind of at the end of the day, it kind of comes down to engineering judgment that ideally you've done appropriate hand calculations. You've done your testing where, it's where you can do testing and where it's conducive for that, so that your engineering analysis just becomes part of a bigger story in your overall analysis. I wouldn't ever trust just a single analysis off by itself without kind of at least some amount of additional either testing or hand calcs, or historical data to provide that insight.
Okay. Meshless methods have been implemented by other CAE software vendors. How is this implementation different from those?
Yeah, so I think just one quick thing is I will say that we don't consider our method to be a meshless method in terms of the noun of a mesh. We definitely have a mesh. The mesh provides efficient computations for stuff like, how are my degrees of freedom ordered? How can I do assembly quickly? So we definitely lean into the fact that there is a mesh. It's just trimmed, and we just generate it without you having to perform meshing tasks. So that's one area that's different from, say, like a paradynamics or a material point method, say, where we really do have a finite element mesh in the Lagrangian form. Um, as far as like these other approaches that don't involve meshing, I'd say that there's a lot of folks who are doing things that are similar. And the only thing I could say is that you should investigate all of these approaches to find what solution works best for you and your team. There are things that we may be very good at that others are not, and there may be things that others are very good at that we are not good at. But I'd say that my general opinion is that if something is a Galerkin method, it's a Galerkin method. And the Galerkin method has been trusted for, I think now something like 80 years in computational work. And it's one of the richest fields um, of computer science. So I think that's the way I would answer that, that it just depends.
Okay. See, maybe we'll take a couple more questions. Someone's commenting that the red cube that we showed earlier reminds him of the Eulerian domain. Does this method have anything similar with Eulerian or coupled Eulerian Lagrangian approaches?
No, it's definitely not. I do see where like the connection comes in. And if you've used Abaqus, you probably are familiar with the Abaqus CE or coupled Euler and Lagrange. It does look very similar, but that is just that red box or that red mesh is just an overview of the scheme that we're going to use to then compute our trimmed mesh. And we use a Lagrangian formulation. We certainly have looked at, and I think we might have some active proposal requests out for various different um, funding sources to look at things like fluid structure interaction. And it's kind of nice that we already have a mesh that kind of looks Eulerian and Lagrangian, but that's not what we have today in this product.
Yeah.
So
Okay, there's some other questions that come in that I think you may have addressed in the course of other answers. So thank you for all of the interest and the questions today. We really enjoyed talking about this stuff. And again, to repeat, what we would enjoy for a next step is we send out a recording of this. We'd welcome a personal conversation with you to see if this technology is useful for you today. As we mentioned, we have early adopter pricing available now. And so if the idea of trying and beginning to use this Coreform IGA for Abaqus approach in your workflow is interesting and exciting to you, we would really welcome you being part of this young community and look forward to continuing the conversation. So again, thank you all for attending and look forward to talking with you again later. Have a great day.